let's now talk about electrons in the periodic table. And again, we are discussing chemistry and we're discussing how these elements and these atoms work because life, on its most basic level, is just chemical reactions, right? The right chemical reactions happening at the right time, at the right place, and at the right speed. Okay, so without chemical reactions, there's no life. And so it's really helpful to understand, especially physiologically, what's going on, if we're understanding the chemistry behind why are these cells going through these specific chemical reactions. So we're going to first talk about electrons and how they work, because that helps us to understand how the periodic table is set up and how that works to organize elements. So we'll be using the Bohr model to talk about electrons. It's a little bit outdated of a model, but it's still helpful for kind of visualizing what's going on with the electrons and understanding their structure and their interaction between atoms. So when we talk about electrons, we talked previously that they're orbiting around the nucleus in these random clouds. But we can use these idea of orbital shells that the electrons spend their time in to describe the structure of an atom. And that's what we're looking at here, right? So these rings, so here's our nucleus, and then these rings are representing different shells that the electrons are spending their time in, that they're orbiting around, they're zooming around in. These aren't hard containers. They're not literal shells, but they give us a sense of the space that an electron is spending time in. Okay, so again, remember, protons and neutrons are in the nucleus, and then these electrons have a -1 charge and are basically massless. Okay, so how does this work? So let's take an example for the element argon to begin with. Remember, at the beginning, in the middle, there's our nucleus. Okay, so that's where we find our protons and neutrons. That's what gives the atom its mass. This first innermost shell will fill up first with electrons. So argon has 18 electrons total. And so the first 2 electrons will orbit around in this first shell. This first shell, the space in that first shell that's available, can only hold 2 electrons. Okay, after that it's full. Any more electrons will be added on to the second shell. This second shell right here, this second orbital right here, that can hold up to 8 electrons. And then once it's full, once this second shell holds 8 electrons, then the electrons move to the third shell. The third shell also holds 8 electrons, right? Typically, for most organic molecules, we don't go beyond the third shell, for the most part. Okay, so 2 in the first shell, 8 in the second shell, and 8 in the third shell. And we'll only fill up the second and third shell once these lower shells, once the first, second, and third shells are full. So fill up those 2 here first, then we fill up 8, and then once that one's full, then we start moving on and putting electrons in that third shell. So you should be able to draw out some of these Bohr models for electron configurations for different atoms. Don't worry about the different colors right now. That has to do with p and s orbitals. We're not going to talk about that. But you should practice, if you know the number of electrons an atom has, an element has, you should be able to draw out a Bohr model representing where are those electrons. So that idea that we were just talking about, where first we fill up the 8 in the second shell and then we move on to the next 8 in the outermost shell, that's what we call the Octet Rule. This will become more important. We'll touch on this again when we talk about types of bonds that atoms can make with each other. But most atoms are looking to fill up that outermost shell, and that process of having their outermost shell be 8 electrons, be totally full, leads to atoms to interact with each other to achieve that state, either by giving up electrons, taking electrons, or sharing electrons. Okay, so that's what we call the Octet Rule. Just keep that in mind as we talk about covalent and ionic bonds later. Okay, so for example, a little bit of preview. Highly reactive elements tend to have they tend to be very close to that octet rule. So like here's sodium, right? So sodium has first it's 2 electrons here in that first shell. The second shell has 8. This third shell has only 1 lone electron. So sodium has a couple options here. Sodium can find or steal 7 other electrons, which might be challenging. Or sodium can donate, give up, send off this 1 lone electron, which basically causes this shell, this orbital, to disappear, which would leave this outermost orbital right here, this outermost shell right here, full of 8 electrons. On the other hand, look over here at chlorine. This shell's full, this shell's full with 8 electrons. This shell, 1, 2, 3, 4, 5, 6, 7. It can hold 8, and it ideally would have 8 in that outermost shell. So, it's pretty convenient. Sodium's trying to give up 1 electron. Chlorine's looking for 1 electron. What do you think is going to happen? That's the basis of an ionic bond, type of chemical bond, getting out of myself, where electrons are exchanged so that way each atom has a full outermost shell. And let's take a look at some non-reactive elements, right? So how many electrons do silicon and carbon have in their outermost shell right now? 1, 2, 3, 4. Remember, this shell can hold 8, so silicon needs 4 more. And carbon, 1, 2, 3, 4. Carbon also needs 4 more. They're both kind of halfway to that full octet rule, and so they will tend to share electrons with other atoms. That's what we call a covalent bond. We'll get there later. So now that we can see how electrons are configured, that's really important for understanding how the periodic table was configured. Periodic table is basically a catalog of elements arranged by their shared characteristics. Okay, it's kind of like a taxonomy of elements, if you would. Okay, so let's take a look at how this is constructed. So we have groups being the columns, top to bottom are the groups, group 1, 2, 3, 4, 5, 6, 7, 8, 30, right. And then going across, the rows are what we call periods. So groups top to bottom, periods going across. Okay, so we've taken some of those groups out. So we've basically taken that big chunk in the middle of those metals. We've taken those out and we're kind of simplifying this. So let's look at some of these atoms. So here in group 1, period 1, we have hydrogen. Hydrogen has 1 electron in its outermost shell, but we still are only in our first shell. Okay, so what do you notice about over here in helium, right? It still only has, even though it has 2 electrons, it still only has electrons in its first shell. In period 1, remember that row going across, the electron shell that those atoms are using in period 1 is just that first shell. Okay, now let's take a look at period 2. What do we see here? What electron shell is being used by atoms in period 2? That second shell, right? That's the outermost shell. Lithium only has 1 electron in there, carbon has 4, fluorine has 7, neon has 8. But they're still only using up to that second shell. What do we see here? Again, period 3, 1, 2, 3, they're now using the third shell. Okay, so the period number basically tells us what electron shell are those atoms using. Now let's take a look at the groups. What trend do you see for group 1? Versus group 14, group 17, group 18. They all share something in common. What is it? 1 electron in the outermost shell, 1 electron in the outermost shell, 1 electron in the outermost shell. Group 14, 4, 4. Group 17, 7, 7. Group 18, 2, 8, 8. So the group number basically tells us the number of electrons that will be in that outermost shell. And that's how we've arranged the periodic table. Because the number of electrons basically tells us the reactivity of that element, and that was what was used originally to construct the periodic table. Alright, let's break it down some more and talk about some general characteristics of some of the atoms in these different groups. So starting over here at the right, so group number 1, remember groups are columns, top to bottom. These are the alkali metals. These tend to be very reactive. They often form +1 ions with a +1 charge, cations, because they have one electron in their outermost shell that they will readily donate and get rid of. Alkaline earth metals are very similar, but they tend to form +2 cations. So cation with a charge of +2. They are also highly reactive, so things like calcium are in here, but not quite as reactive as the alkali metals. These two tend to not, we don't really find them in their pure form, just like a chunk of sodium lying around, because they are so reactive. They'll react with water molecules in the air, right? Exchanging electrons. So we don't often find them in their pure forms. This group right here, transition metals, these are mostly all kind of grouped together because they're fairly unreactive. They don't, so meaning that they don't often exchange electrons with other atoms. They tend to be malleable but have really high boiling points. So we can heat them up, we can make them into sheets, we can form them into columns, different structures, right? But it takes a lot of heat, a lot of energy to get them to actually melt. The other good thing that we have discovered about transition metals is that they conduct electricity and heat very well. Okay, so we can move electricity through a lot of these transition metals very easily. These over here are kind of a group of misfits. These are a mix, groups 13 through 16 are a mix of metals, metalloids, non-metal solids that tend to be very brittle but gain electrons easily. Especially these ones over here, kind of in like this area, tend to make covalent bonds, sharing of electrons. Yeah, so these ones here are kind of a mix of different characteristics. It's hard to kind of classify them. Here we have the halogens. They tend to form anions, negative anions, which like to react with the positive cations over here, the alkali metals and the alkali earth metals. And these over here are the noble gases. We call them noble gases because they're unreactive. Because remember, if we, that last image we looked at, they have a full electron shell on their outermost shell, so they're satisfied basically. They don't need to gain or lose any electrons in order to achieve that octet rule. Other general trends that we see in the periodic table, as we move down the groups, the atomic radius increases, and as we move from right to left. Okay, so the atomic radius, basically how large that atom is, increases as we move from right to left and from top to bottom. As we move from the left side, group 1 over here, to group 17, the electron affinity increases. So how readily that atom will steal electrons from another atom. You're more likely to have atoms over here steal electrons than other atoms over here. That also increases the ionization energy though, how much energy it takes for that atom to form an ion. We also see a trend decreasing metallic characteristics from bottom left to top right, and opposite. From the top right to the bottom left, we see an increase in metallic characteristics. So kind of based on where an element is on the table, we can make some assumptions about how it will react, how it deals with electrons, how large it is, things like that, its characteristics. So for us, in our class, we are going to be mostly not a lot of times dealing with the transition metals. So this is an image of the periodic table with that big middle section of the transition metals kind of cut out. And we're usually going to be kind of hanging out kind of in this area right here. Carbon, nitrogen, oxygen, phosphorus, sulfur, chlorine, fluorine, hydrogen, some lithium and sodium, magnesium, calcium, potassium. These are the elements that tend to be very common in organic molecules. And what we're going to dive into next is how these different atoms, how these different elements react with each other to form molecules. And again, all that reaction happens with the electrons.